Welcome to our next section of elementary statistics. In Chapter 3, we're dealing with 3.4, measures of position and outliers. We're going to look at what z-scores are, interpret the percentiles. We're going to look at quartiles and interpret the interquartile range, IQR, and check a set of data for outliers. Our first objective is to determine and interpret z-scores. A z-score is it represents the distance that the data value is from the mean or the average in terms of the number of standard deviations. We find it by subtracting the mean from the data value and dividing this result by the standard deviation. Sorry, I'm having some problems talking. Of course, as we've seen in other calculations, there's both a population z-score and a sample z-score, depending upon if we're looking at the entire population of a category. Then we have x minus mu over sigma, mu being the mean, and sigma being the standard deviation if we're looking at the entire population, or if we're looking at a subset of the population, and just taking a sample of that, then we have x minus x bar over s. Again, x bar being the mean of a sample and s being the standard deviation of a sample. The z-score is unitless. It doesn't have measures. It has a mean itself of 0 and a standard deviation 1. So let's look at an example. Determine whether the Boston Red Sox or the Los Angeles Dodgers had a relatively better run-producing season. So in this season, we see that the Red Sox scored 876 runs, while the Dodgers scored 804 runs. And then here we're given the measures of the mean, 731.2, and the standard deviation, 72.6 for the Dodgers, and 710.8 and 60.2 for the standard deviation. So we compute each team's z-score, and we're going to round it to 2 decimals. So for the Red Sox z-score, we get 1.99. You can see all the measures there. X minus mu over sigma, x minus mu over sigma, x mu sigma, x minus mu over sigma for the Dodgers, x mu sigma for the Dodgers. So our two scores are 1.99 and 1.55. And what this means is that the Red Sox had a run production 1.99 standard deviations above the mean, while the Dodgers had a run production 1.55 standard deviations above the mean. So what this means is that the Red Sox had 2 standard deviations above their average, while the Dodgers only had 1.5 standard deviations above their average. Therefore, the Red Sox had a relatively, and this is important, relatively better year at scoring runs than the Dodgers when you compare it with their historical averages or means. Our next objective is to interpret percentiles. Okay. The kth percentile, denoted by P sub k, of a set of data is a value such that k% of the observations are less than or equal to the value. So notice here at P sub 2, what this means is that 2% of the observations are less than or equal to P2. If we go out to P99, what this means is that 99% of the observations are below P99, this point here, or 1% is greater than 1% of the observations are greater than the P99 value. Okay, it's a little bit confusing, but it's just saying the percentiles are just saying that that point is greater than or equal to whatever the value of k is of of the observation. So let's look at an example. This may help. Jennifer just received the results of her SAT exam. Her SAT mathematics score of 600 is in the 74th percentile. What does this mean? Being at the 74th percentile means, and this would be P sub 74, means that 74% of SAT mathematics scores are less than or equal to 600. And 26% of the scores are greater. So again, remember we're at 74, P74. So 74% of all the scores are less than or equal to that measure, 600. And the other side of it, what makes up 100%, 26% of the scores are greater. Okay? It's important the less than or equal for percentiles is the whatever the PK value is, and then of course the ones left over after the 100% are greater than. So 26% of the students who took the exam scored better than Jennifer. So now let's look at quartiles, a specific breakdown of percentiles. Quartiles divide data sets into fourths or equal parts. And so we have, of course, a quartile is 1/4. And so we have quartile 1, quartile 2, quartile 3, and we don't do quartile 4 because that's all of the data. So quartile 1 is greater than or equal to 25% of the data. Quartile 2 is equal to 50% is equal to or greater than 50% of the data, and quartile 3 is equal to or greater than 75% of the data. The first quartile, Q1, divides the bottom 25% of the data from the top 75% of the data. Therefore, to find quartile 1, this is equivalent to the 25 percentile that we saw in the last problem. The second quartile divides the bottom half of the data from the top half of the data, 50%. So the second quartile is equivalent to the 50th percentile. Notice this is equivalent to the median of all the data. The median is the second quartile. The third quartile provides the bottom 75% of the data, divides the bottom 75% of the data from the top 25% of the data. So the third quartile is equivalent to the 75th percentile. So how do we find quartiles? First, put all of the data in ascending order from smallest to largest. Then determine the median, M, which is equal to the second quartile. This will give you the first quartile, this will give us our first quartile measure, which is the second quartile. Step 3 is we're going to divide the data set into two halves. The observations below, to the left of M, and the observations above the median. Okay? The first quartile is the median of the bottom half of the data. And remember, the median is the middle value of all the data. Or it's the average. If all the data in that sample is even, then we take the average of the two middle values. And the third quartile is the median of the top half of the data. So now let's look at an example going through this. The Highway Loss Data Institute routinely collects data on collision coverage claims. Collision coverage insures against physical damage to an insured individual's vehicle. Collision covers your car, okay? Comprehension insurance covers the other person's car and any injuries. The data in Table 16 below represents a random sample of 18 collision coverage claims based on data obtained from the Highway Loss Data Institute. Find and interpret the first, second, and third quartiles for collision coverage claims. Now remember, the first step is for us to redo this data in ascending order from the smallest value, looks like 370, there it is, to the largest value. I see a 21,000, maybe that's it. So here's the data, column 1 and then, row 1 and then row 2, from smallest 180 to largest 21,000. Okay? Then we calculate the median of this data. Since there are 18 observations, we take the two middle values, which are 1657 plus 1953, and then we divide them by 2 because we're finding the average between them. Because the median value is halfway between these two values, and so we get 1805, and this is our median, which is also our quartile 2 marking. Step 3, the bottom half of the data is the first quartile, and that was the first row we saw in the last chart. The median of these data, because it's 9 data points, is simply the one in the middle, which is the 5th observation. You can see all the points here from that first row, all 9 points. The middle one, the median of that data, is 735, so this is quartile 1. We do the same thing with the top half of the data, which is quartile 3. Again, we have 9 observations, so we're going to look for the middle observation. This will be the median, and we get 4,668. The last part of this is to interpret those, and the interpretation means quartile 1 is at 735, so 25% of the collision claims are less than or equal to $735, while 75% of the claims, what's left over in the 100%, are greater than that. For quartile 2, remember this was the median that we calculated with the average of the two middle values. 50% of the collision claims are less than or equal to 1805, which is the second quartile, and 50% of the claims are greater. And lastly, 75% of the claims are less than or equal to 4,668, which remember was quartile 3. And if 75% are less than or equal to, that leaves 25% left that are greater than this mark. Here we're doing the exact same problem as we did before, but this time we're going to use technology to calculate all the quartiles at once, specifically StatCrunch. I've included a video here. Hopefully it will play, and if it doesn't, you can go to the PowerPoints and just watch this video. It's only a minute long, or you can just go to YouTube and search for StatCrunch, find quartiles, IQR, etc. Basically what you're doing is once the data is input into StatCrunch, you're going to go to columns, select the column your data is in, then go to statistics summary, and make sure you include the IQR because it's not included in the summary list. When we do this, we see that we got the exact same measures that we got by hand from StatCrunch. Here's Q2, which is the median, Q1, which is 735, the first quartile, and quartile 3, which is 4668. I'm going to try to play the video now, and hopefully you can see it.
Here we're going to use StatCrunch to find the quartiles of this. It's pretty basic. Just come up to there, open in StatCrunch. Data opens, and then you're just going to go to Stat, Summary Stats, and Column. Choose the variable the numbers are in. Click Next. And then you just got to make sure that you choose the IQR because it's not part of what's returned right away. So choose IQR so that that's there. Then click Calculate. Now you're going to see that the quartile 1 is returned to 3 decimal points, the quartile 3, and the IQR. But where's quartile 2? Well, remember, quartile 2 is the median. Then to get the lower and upper fence, basically you got to just take out a calculator. And you just got to calculate this. You have the IQR here. So you take the quartile 1 minus 1.5 times the interquartile range. And you do quartile 3 plus 1.5 times the interquartile range. So that's your lower and upper fence. You got to do it on the calculator. Or you can program it in there, but it's pretty basic on a calculator once you have this data, because it doesn't show it in this box.
So here what we're looking at is actually how, if we use a different program, specifically Minitab, notice that our quartile 1 and our quartile 3 don't match up with our information that we found by doing it by hand or with StatCrunch. And the difference here is due to the fact that StatCrunch and Minitab use different algorithms for obtaining the quartiles. So this to me again leads us to focus on one instrument and StatCrunch, which is matching our hand calculation. So let's use that. Our next objective is to determine and interpret the interquartile range. The interquartile range, IQR, is the range of the middle 50% of the observations in a data set. So it's that range of information that's between the first quartile and the third quartiles, and it's found by simply using the formula IQR equals Q3, the third quartile, minus Q1, the first quartile. So as an example, let's determine and interpret the interquartile range of the collision data from an earlier example. So again, what we had here is just to the third quartile, which was 4,668 in the last problem we just did. And the first quartile was 735. We subtract those, and we have values that are in the range of $3,993, which is the range of claims in the interquartile range, in the middle half of the range. The range of the middle 50% of observation in the collision claim data is $39.93, and it's just the dollar value of all the, well, in this case it's the dollar value because they're claims, the data is dollars, but it's just it's the value of all the numbers between the first and third quartile, or all the data that's exactly in the middle of your study or chart. Determining and interpreting the interquartile range. So let's look at the overall data from before. So the mean collision claim is 3874, and the median is 1805. We say the median is more representative of the center because the data is skewed to the right. Notice that only 5 of the 18 observations are greater than the average. So this means there's more data to the left, so that the graph is skewed to the right. This has always been a little bit confusing for myself as well. So 5 of the 18 observations are greater than the average. So that means more data is to the left, which means our graph is skewed to the right. Strange, I know, if you're putting it in ascending order, I'm talking. So the total data range is 21,147, the highest value, minus 180, which is the lowest data value, which gives us $20,967. The standard deviation is $5,301, and the interquartile range is $3,933. The values of the range and the standard deviation are affected because there is one extreme claim, this really large value. You see a huge difference in this range, which is almost the value of the largest claim. So you can tell that we have a very small claim and a very large claim. So it's likely that the data is going to be skewed right or left anyway when you have that kind of data discrepancies in each one. So the values of the range and the standard deviation are affected by that extreme claim, that one claim that's really out of bounds of the other claims. It's not close to the other claims. When the distribution of data is highly skewed, or it contains extreme measures, it is best to use the interquartile range as the measure of dispersion because it's more resistant. Okay, and so that's why we're using that middle range to explain what's happening with our data. So which measures do you report? So if you have a symmetric or bell curve, we're going to use the mean for the measure of central tendency, which is the average, and a standard deviation. But if we have a data set which is skewed left or skewed right, then we're going to use the median as the measure of central tendency and the interquartile range as our measure of dispersion. This is a really important table. Make sure you get this in your notes so you know which one to use and how to use it. So just to reiterate that last table, which I've included on this slide again at the bottom, when you're given the instruction to describe the distribution, this means to describe its shape, which is either symmetric, skewed left, or skewed right. Its center, mean or median, and then its spread, standard deviation or interquartile range. And again, this table, like I said, is really important because it tells you which of the measures to use depending upon the shape of the distribution. But also it's important to remember that when you're describing the distribution, you're describing its shape, its center, and its spread. Our final objective is to check a set of data for outliers. Outliers. When performing any type of data analysis, we should always look for extreme observations in the data set, numbers that are really outside kind of what the bounds are, either really high or really low compared to most of the answers. Extreme observations are referred to as outliers. Outliers can occur by chance because of error in the measurement of a variable. In the measure of the variable, they can occur during data entry or from errors in sampling. But notice here, it is possible for the outliers just to be an actual value. As we saw with the claims, there was just one really large claim, maybe a very expensive car, okay? But often outliers are caused by some kind of error in collection. And so we definitely want to check that, and is one of the checks that you would do in going through any statistical analysis. How do we check for outliers? By using the quartiles. Well, first we determine the first and third quartiles of the data. Then we compute the interquartile range. Okay, remember this is that middle 50% of data from quartile 1 to quartile 3. Then we determine the fences. Fences serve as cutoff points for determining outliers, and this is how you're actually going to determine. This is a scientific way, a standardized way of determining that you have extreme data or outliers. And so our lower fence is the first quartile minus 1.5 times the IQR, where the upper fence is the third quartile plus 1.5 times the IQR. Then once we have this data, what we're looking for is any values that are less than the lower fence or greater than the upper fence. So those values that are below the lower fence or above the higher fence, upper fence, these are what we would consider to be outliers. So our last example, our last slide here in this deck is to check for outliers. Check the collision coverage claims data in Table 16 that we've been using throughout this chapter and section for outliers. Well, first we have to go back and look at what our first and third quartiles are, right? And from previous examples, quartile 1 was 735 and quartile 3 was 4,668. Remember, our interquartile range, IQR, is Q3 minus Q1, which equals 3,993, 4,668 minus 735, okay? At this point, what we need to do is calculate our fences, right? So the lower fence is quartile 1 minus 1.5 times the IQR, or 1.5 times 3,993. 735 minus 1.5, which is roughly what that's 4,000. So half of 4,000 is 2,000. So it's 735 minus roughly about 6,000. And we can see there we get negative 5,164.5. These are all dollar amounts because the data is in dollars. It's claim amounts. The upper fence, UF, is the third quartile plus 1.5 times the IQR. So it's this plus about 6,000, which we can see is $10,567.50. Now remember, what we're doing is we're trying to find the outliers, which is our last step. And so we're looking at any data points which are below the lower fence. Well, our lower fence is negative. I certainly don't think there are any claims of negative dollar amounts. That means that you as the insured are going to pay the insurance company to fix your car. Ain't happening. So we know there aren't any lower fence outliers below the lower fence. But then we look for any amounts that are larger than $10,567. And there is one observation, which we noted in the last slide or two, and that is that there was one claim that was $21,147. And so there's only one outlier in this data.